Hello everyone, in this lecture we will cover one last functional equational form, and this time our condition is given in multiplicative form, and it is defined for our domain is positive real numbers, and it's mapped onto all real numbers. So therefore our function is only defined for positive real numbers. Moreover, we would like to find only monotone functions, either monotonically increasing or decreasing functions. So we will start for obviously x greater than 0. In this case, f of x can be written as using the previous trick we got earlier, greater than or well, obviously, okay, so hold on, let's do it in two steps. So that would be equal to f of square root x squared, but that's obviously greater than or equal to 0. In addition, you also know that f of 1 can be written as f of 1 times 1, which is by this multiplicative form, f of 1 times f of 1. So therefore this immediately implies that well, obviously f of 1 square minus f of 1 is equal to 0, or equivalently you can say f of 1 times f of 1 minus 1 is equal to 0, suggesting that f of 1 is either equal to 0 or 1. Now we have two cases obviously again. So in the first case, if f of 1 is actually equal to 0, then that would imply that f of x, as we did previously, can be written as f of x times f of 1, but f of 1 is simply equal to 0, suggesting our function is the zeroth function, and sure enough it works for all x strictly greater than 0, I should say. So therefore definitely it satisfies this condition, but that's not an interesting case. The second case, which is the interesting case for us, is the case when f of 1 is actually equal to 1. Then in that case, f of x must be greater than 0 for all x greater than 0, and for a good reason, because notice that if f of x is actually equal to 0, say f of x is actually equal to 0 for a value of x in this range, then this implies that, well, f of 1 can be written as f of obviously x times 1 over x, which is again equal to f of x times f of 1 over x. And for that f of x which make it equal to 0, that whole thing would be equal to 0, but that's a contradiction because we claim that we are in the case where f of 1 is not equal to 0. In fact, it's equal to 1. So now we will go ahead and make use of a new function. Let's define function g, this time from all reals to all reals, negative or positive doesn't matter, such that g of w is simply equal to ln natural logarithm of the function f and f of e to the power w. From this it is obvious that, so let's see if we can find out the additive form of the Cauchy equation. G of x plus y by definition is just ln f of e to the power x plus y, but that's simply ln f of, we can split it, e to the x times e to the y, but then the function f is in multiplicative form, so therefore I can write it as ln f of e to the x times ln f e to the y, and then the property of the ln function will split this into two, ln f to the f of e to the x plus ln f of e to the y, but this is just g of x plus g of y. So therefore what we did is we showed that the function g is of the Cauchy additive form of the Cauchy equation. Also knowing that f itself is a monotone function implies g is also a monotone function. So we have a monotone function. it has an additive form. Therefore, the solutions, that would imply that the solution will be g of w is equal to cw for a c, so for all w, and c is obviously g of 1. But if that's the case, let me scroll down a little bit. So if that's the case, that would imply, given this form, so if you replace it cw here, and we can take the exponent of both sides, and obviously you get f of x equals x to the power c for x greater than 0 for all w set, but then because of our definition, x must be greater than 0 as it turns out. So that beautifully solves this problem, and I leave it to you as an exercise to check that this solution here, f of x to the power c, sure enough satisfies our equation, and we're done.